Hi again. Would like to begin by sharing the Canvas homepage. So I'll do that now. I hope you can see the Canvas homepage at this point. I believe you can. There you go. In this page, if you move to the modules link, the one where the cursor is currently at, you'll notice that I have uploaded, not just for the first two modules, but now for the third module, a lot of different notes and presentations and demos of how you use StatCrunch, how you apply the concepts embedded in chapters 5, 6, and 7. Earlier, I sent you a video presentation of how all three chapters present a part of the course whose narrative it is to introduce you to the study of uncertainty and the study of risks. And this video in particular will focus its attention on randomness, the concept of randomness, the concept of the law of large numbers, and how we measure probabilities. In our following videos, we will then employ probabilities in a quantitative, random setting in order to compute what we call expectations and standard deviations, which are our measures of what to expect in quantitative random situations or situations of uncertainty that can be measured quantitatively, and also what we then call risk measures. And with these three measures, probabilities, expectations, and deviations, we will then be able to create an understanding of the nature of uncertainty in various different situations that we refer to as models. So we will cover models of probabilities that are introduced to you in chapters 6 and 7. So let's begin. I will begin with a whiteboard. And what you will notice in this whiteboard is that, again, we're interested in measuring uncertainty. Uncertainty means not knowing what will occur next. By implication, the term of uncertainty implies that that we do know something. We can define the nature of the uncertainty with the concept of event. And then we can, following that concept, lay out the possibilities of the resolution of an event, the outcomes of the event. And once we have a possible list of outcomes, these outcomes can occur in sequences or can occur one at a time or only one time. And by accounting for the list of how these outcomes may occur, including repetitions, create something that we call a probability space. And a probability space is a mathematical construct. It's a construct that allows us to then measure the actual probabilities of an event, the actual probabilities of all the outcomes of an event. And then specifically, we'll talk about the 9 rules of these metrics, of these arithmetic concepts. So let me give you an example. An event could be something like the Super Bowl. In a Super Bowl event, there's 2 teams, and either Team 1 can win, Team A can win, or Team B can win. Somebody's got to win the Super Bowl, one team or the other. Even if they have to go to overtime to decide, one team has to win. So in the case of the Super Bowl, either Team A wins or Team B wins. Those are the only 2 outcomes possible. And because the Super Bowl is only played once per season, the probability spaces of the event are the probability space of the event is the same as the outcomes listing. So this is what we usually refer to as a simple event, because those two aspects are identical. And then if we don't know anything about, if we don't have any internal information about the offense, the defense, the individual superstars playing in key positions in defense and in offense, then we might say that the game is a coin toss or a toss-up, in which case the probability of A and the probability of B will be equal, and by construction they will have to be 1/2, one out of two possibilities, or 1/2. Or as we say in odds, in the measurement of odds, we call that a 50-50. A 50-50 is how we characterize the odd probabilities as odds. So that would be an example of this list of concepts that allow us to construct from basic principles a probability set. And we use these kinds of constructs, event, outcomes, probabilities, space probabilities, and odds, this 1, 2, 3, 4, 5, in situations where we don't have this the ability to replay or reestablish events. Unlike, for example, a coin toss, a fair coin toss. In a fair coin toss, you have two possibilities, heads or tails, and the probability space looks the same. It also looks just like the list of outcomes, heads or tails, because there's no advantage for either one or the other occurring. And in this case, the probability of heads and the probability of tails in a fair coin situation is, again, 1 and 2, or 0.5. And the odds of the event would be referred to as 50-50. The probability that heads occurs is 50%. The probability that heads doesn't occur is 50%. So we call those the odds. As opposed to two fair coins tossed. What happens when two fair coins are tossed? Well, the outcomes are still heads or tails, except that since we have two coins, the probability space, the relevant probability space now looks a little bit richer. It could be heads, heads. It could be heads, tails. It could be tails, heads. Or it could be tails, tails. And so everything that could happen has a 1 in 4 chance. So the probability, for example, of tails, heads is 1 in 4 possibilities. And we would then say that tails, heads, the odds of tails, heads is 3 to 1 against. So what does 3 to 1 against actually refer to? 3 to 1 against means that for every 4 coin tosses, we would see tails, heads expectedly 1 time, and we wouldn't 3 times. And so there's 3 times more likelihood of not seeing tails, heads for every 1 time or 1 time occurrence of this outcome happening upon many, many, many repetitions of the event. So odds, the calculation of odds, comes from something that is called the law of large numbers. And the law of large numbers simply says that if you have an event that can be properly defined in this kind of manner, where you have repetitions of the event and where the structure remains the same one repetition after another, where the probabilities that underlie the structure of the event and the outcomes is what we call independent from just one try to another and identically distributed per try. We then can use the law of large numbers to translate probabilities into what we call odds, and thus the birth of a complete industry, an industry called the gambling industry, very old industry. In Roman times, the way Roman politicians kept the people entertained was through gambling. In today's modern world, we keep people entertained with game-like structures, gambling game-like structures, whether it's gambling at sports books in casinos, or whether it's through the gambling that occurs in the stock market, or in any environment where a lottery, any environment that keeps your mind occupied with the notion of taking a situation under uncertainty and quote-unquote beating the odds and benefiting monetarily or materially from correctly guessing what comes next based on these structures. So once we have a good understanding of how events can be defined so that we understand what are the possible outcomes of the event and what is the layout of the occurrence of these outcomes in a probability space, we then develop 9 rules that teach us how to help us compute these particular probabilities. So I'm going to describe quickly the first 4 or 5 of these because they're pretty simple. And then in future videos, I'm going to talk about one video which is about something called the multiplication rules of probability, which are 2. Another one called the addition rules of probability, which is another 2. And then we'll talk to you about, in a 4th video, about the conditional rule of probability, something really important in building what's called artificial intelligence systems, something really important in something that we call machine learning in today's modern world, and also something called the decision-making in artificial systems. So those are modern day applications of these 9 rules of probabilities introduced to you in chapter 5. So here we go. First rule. The first rule of probability is called the basic rule of probability. And all the basic rule of probability says that an outcome, any kind of outcome, will always have a probability that falls in the range of 0 to 1, inclusive. Meaning, when the probability of an outcome is 0, we call those events impossible. When the probability of an outcome is called 1, we call that a sure thing. And when we call the probability any other value between 0 and 1 exclusive, that's a reflection that there's something else about the event, some secondary outcome that is possible, and that we will end up calling in rule 3 the complement outcome. So the basic rule simply says that under uncertainty, an event will have outcomes, and these outcomes will have probabilities, and their numeric value of the probabilities will be between 0 and 1 numerically. They can be expressed as percentages, as fractions, as decimals, but they'll always have a numeric value that is fractional between 0 and 1 inclusive. The second rule is called the overall rule. And the overall rule just says that an event with multiple outcomes, call these outcomes a list of x's, like x1, x2, etc., will have probabilities for each of these distinct outcomes. We'll call them P1, P2, etc., such that their sum is equal to 1 or to 100%. So all the overall rule of probability says, rule number 2 says, is that when you take into account all possible distinct outcomes of an event, the sum of all their probabilities will equal 1.0. That's the overall rule of probability. Third rule is called the complement rule. And the complement rule of probability says that an event can be broken up into a binary choice where something occurs or it does not occur, like to be or not to be. And so the probabilities of the event A plus the probability of anything that is other than A, that is known also as the complement of A, must be equal to 1 by the second rule of probability. Okay. And this is pretty useful because sometimes we can back into an answer, but not by knowing the probability for it, but rather by knowing for the probability of it not occurring. So the probability of A can be inferred sometimes as the complement of the probability of not A. So that is a consequence of this complement rule. And the fourth rule of probability is called the marginal rule. And the marginal rule of probability is a rule that states that the probability of an outcome of an event is such that we can calculate it by measuring a count of the number of ways in which A can occur and divide that by a count, by another count. Divide that by the count of ways of all things, the count of the space of probability, the count of the size of the probability space. And that constitutes the first 4 rules of probability. So it's a count divided by another count. That was the way in which we actually engaged into the 3 examples in this video, 3 earlier examples in this video, that are part of this particular note set that we've been building thus far. I hope that this video enables you to begin your journey through Chapter 5 conceptually. What I will do over the next video is discuss the other 5 rules that remain out of the 9. The 5 rules that remain are, 1 is called the marginal rule of probability. That's coming up in our next video. The next item after that will be a video introducing you to the addition rule of probability and another one for the multiplication rule of probability. So we will learn to use this logical 6-stage or 5-stage way of identifying probabilities and develop 9 rules that can help us compute pretty much the odds of anything that is subject to uncertainty. And what I'd like to do for now is stop this video. Thank you for watching, and I hope you watch the remaining 3 videos on Chapter 5 of this series of calculations.